Hello student, today we're looking at section 8.2 from the Nelson textbook, and in this I'm going to answer a couple of questions for you. That way it gives you a better understanding of mechanical waves. Let's get started. In your own words, describe the characteristics of the two basic types of mechanical waves. Make a label diagram of each. First, let's start off with waves, and recall the waves is the transfer of energy. And from waves, we can transfer energy through a medium or not a medium. So we can break the type of waves into two different categories. If they do require a medium, we call those mechanical waves. And those that don't require medium, those will be non-mechanical waves. So mechanical waves are the ones that do require a medium, and the two basic ones that we're going to study are transverse and longitudinal. There is the third type, which is complex waves, and those are just a combination of transverse and longitudinal. We're going to be looking at that a later question in this, but for now let's just focus on the transverse and the longitudinal waves. Now, the way that you can distinguish between the two, you need to know in which direction the energy is flowing and how the medium behaves. In particular, how are the particles being displaced? And for comparison purposes, I'm going to put the energy flow for both of these to be to the right, and that way we can focus on the particle displacement. So in the transverse wave, the particle displacement will be perpendicular to the energy flow. Whereas in the longitudinal wave, the displacement of the particles are parallel to the energy flow. So let's think this for a moment. We have a medium, and in this medium we added some energy, and as the energy travels through the medium, that's what we call the wave. But once the particles get the energy, then they're able to have a displacement. So as the energy gets into the particle, they are displaced. But then the medium brings them back into equilibrium. So after the wave has passed through, the particles go back towards equilibrium. So one way to look at the displacement is that these particles are going to be going, for example, up and down for transverse and right to left in longitudinal. So we have to include the dashed line to show that these particles don't travel with the wave. As the wave travels in one direction, the particles oscillate back and forth they oscillate back and forth relative to an equilibrium point. So that's why we can call this parallel for longitudinal and transverse perpendicular. Provide two examples of transverse waves that you have encountered in everyday life. Explain why each example is considered a transverse wave. So the plane just went by. The plane, I was able to hear it because of sound waves. Sound waves are actually longitudinal, so that wouldn't be a good example. So for transverse, we can think of other examples, and the simplest one, maybe not the simplest one, but a good example is if you think of a lifeboat. And here we have the person is on the water, and as the water comes to the right, this particle or the person is just going to bob up and down. So this will be an example of a transverse wave. So a person bobbing up and down as the waves are passing through it. Maybe the most common example that you look at is going to be a string. So another example of a transverse wave would be a person that's acting on the string, making just the string go up and down like a skipping rope. So in both cases, the energy flow was to the right, which is the wave, but the particles were being displaced up and down. So that's what makes these a transverse waves. For question 3, provide two examples of longitudinal waves that you have encountered in everyday life. Explain why each example is considered a longitudinal wave. Well, as we saw before, as an airplane is going by, I'm able to hear the airplane because of the sound waves that are produced. So what that causes is there's the oscillation happening among the air particles in the air. And we know it's a longitudinal wave because we could calculate the pressure differences, and we have areas of low pressure and areas of high pressure. So as I mentioned before in the lesson, it is really hard to measure the number of particles and measure their displacements. So instead, for sound waves, what we do, we look at the pressure differences in the air. So for these pressure differences, they go back and forth between low pressure, low pressure, high pressure. And then they even have a better name. So for the low pressure, we have very few particles in that area. So we say that this is a rarefaction region. And the areas of high pressure, we say that this is where the compression occurs. So that's what distinguishes longitudinal waves. We have high pressure, low pressure, high pressure, low pressure, and those are repeating themselves through cycles, which is what we call a wave. So one cycle from low to high. Another example of a longitudinal wave. Well, the most common in a physics classroom will be a slinky that's on the floor and it just gets pushed to the right, and then we see these rings go back and forth. And here we see that the rings, the number of rings on a slinky, it has regions of compression, where the slinkies are much closer towards each other, and areas of rarefaction, where the slinkies are further apart. There's fewer of them. So this is what is required to be looking at longitudinal waves, compression and rarefaction, which looks at the less particles or more particles. And you can think about pressure as well. Now questions 5 and 6 I put together because they're very related to one another. So they want us to define sound and explain how a medium can transfer sound waves efficiently. So we could say air, or it could be other mediums, because you could also put your ear right next to a metal and then you could hear the sound. So it could be produced by more than just air particles. And how can sound waves transfer energy efficiently? Well, we looked at that before. We can increase the number of particles, we can increase the energy of the particles, and we can also reduce the area where the particles are found. So that was 3 things that we can do to the medium itself. So by exciting the particles more, I really mean have a higher temperature, because faster moving particles are going to collide more likely than slower moving particles. If we increase the number of particles, collisions increases, and as we reduce the area, collisions increases too, because sound passes energy through collisions. So in this case, sound is a mechanical wave. How can I explain my answer? Well, that's how we define sound to begin with, so that's a very difficult question. But maybe if you think about outer space, or reducing the number of air particles and trying to speak, assuming you can stay alive, then you wouldn't be able to hear a sound. By the way, that was an attempt at a joke. Question 7. Aside from communicating by speech, list 3 benefits of being able to detect sound. I mean, the easiest one, if we think about hunters and gatherers and predators and prey, to detect sound, well, deer will be able to detect sound in order to be aware if there's a predator nearby. But the reverse will also be true, right? Predators to locate prey. For example, a bat. Well, now that we're thinking about bats, another benefit would be to think about maybe daredevil. Right? What does the daredevil do? He hits a stick on a surface, and that surface, the waves reflect, and those waves, they make it back to his ear. So there's a form of another way to detect sound, because the daredevil in the Marvel series is not able to see, but he can hear, and then based on the location of the objects, he can visualize the room. Now you might want to look up this famous person called Daniel Kish, and he's the daredevil per se in our modern day world. So take a look at him. Or even there are other people trying to detect sound in other ways and become cyborgs. So that could be something interesting that you want to look up as well. So there's people who can detect sound by putting implants into their body, and then that way they can hear other sounds that other people cannot. So we could detect sound to take us to the next level of humanity, to become cyborgs. So that could be interesting too. Question 8. Provide 2 examples of a complex wave motion. Describe the wave motions and explain how you know that transverse and longitudinal waves are present. This one's quite easy. For complex waves, the common example that you can think about are water waves, because for water waves you have particles moving left and right, up and down, so it's a combination of longitudinal and complex wave motion, right? Because here, if we assume that the energy flows to the right, some of the particles are moving up and down and other particles are moving right and left. So that's why we say by complex motion. So it's made up of longitudinal and transverse. Another example, maybe you never thought about, is someone hitting another person on the face. And on the surface of the skin, we're going to have transverse waves because the energy is going along the surface of the skin, but then the displacement of the particles are up and down. But we also have longitudinal because the person feels the pain inside of their cheeks as well. So the motion is also going in. So this would be another type of complex waves. Another example that I'm not sure would be complex would be the combination of earthquakes, where they have both what are called S and P waves, which is both longitudinal and transverse type. But I'm not 100% sure if they're considered as one. That could be your own research. So again, complex waves, they're made up of longitudinal and transverse wave motion, which is why we say makes them complex. And for completeness, we say it's transverse along the skin, along the surface of the skin, and longitudinal going into the face for the punching someone in the face. And the last example here, question number 9, figure 6 is an image of an electric ringer inside a bell jar. A vacuum pump can be connected to the jar. You turn the ringer on and slowly start removing the air from the bell jar. Then you slowly allow the air back in. Predict how the sound from the ringer will change as you remove the air and then as you allow the air back in. Well, as you remove the air, you should be able to hear less sound, and as you put the air back in, you should be able to hear the sound once again. And to explain why the sound will change, well, because sound is a mechanical wave which requires a medium. So if we have less of the medium, we should be able to hear less of it. You could think about this in outer space. So in outer space, if you were to try to talk in outer space, you wouldn't be able to hear anything because there's no sound particles, there's no air particles in space, right? That's why we have the suits. So that's really interesting. There's a lot of movies where they show people being able to speak, or like objects making sound as they're moving in space, but technically they shouldn't make any sound because you need air particles to make sound. So whenever you're traveling in space, it's actually going to be a really quiet journey, and could be sad but exciting at the same time. So let's just write down our answer so that way we can have it for completeness sake. Alright, so as we said, as we decrease the air particles in the jar, the sound will decrease, and as we increase the air once again, the sound will then begin to increase. This is due to sound being a mechanical wave which depends on the air particles. And you could take it to the extreme that if there were no air particles, then you wouldn't be able to hear a sound, just like in space.